Imagine the vacuum of space, the total emptiness, right? Well, not quite. Even in the darkest voids of space, there's a background energy at play. It's called vacuum energy, and it's everywhere. We're talking about the zero-point energy of the quantum vacuum. Sound complicated? Hang tight, I'll break it down for you. Now, vacuum energy isn't just a theoretical idea, it has real, measurable effects. One of the coolest examples is the Casimir Effect. Discovered by Dutch physicists Hendrik Casimir and Dirk Polder in 1948, this effect causes a tiny attractive force between two metal plates placed very close together. It's like a cosmic nudge from the vacuum energy itself. The Lamb shift and spontaneous emission are other phenomena influenced by vacuum energy. These effects have been observed and experimentally verified, reinforcing the idea that vacuum energy is as real as electrons or magnetic fields. But hold on, because it gets even crazier when we talk about black holes. Stephen Hawking hypothesized that vacuum fluctuations create particle-antiparticle pairs near a black hole's event horizon. If one of these particles falls into the black hole and the other escapes, the black hole loses mass. Over time, this process could lead to the black hole's evaporation. We're talking billions of years, but still it's mind-blowing. So, why should we care about vacuum energy on a cosmic scale? Well, according to general relativity, energy and mass are equivalent. If vacuum energy exists, it should exert a gravitational force. Now, there's a bit of a mystery here. Theoretical predictions of vacuum energy suggest a value that's astronomically large, like 10 to the power of 113 joules per cubic meter, but observations and the upper limit of the cosmological constant suggest a much smaller value. This discrepancy is known as the cosmological constant problem or the vacuum catastrophe. It's a puzzle that scientists are still trying to solve. Before we dive deeper into quantum field theory, let's take a moment to explore a fundamental concept: zero-point energy. Zero-point energy, or ZPE, is the lowest possible energy that a quantum mechanical system may have. Unlike in classical mechanics, where a system at its lowest energy state is completely still, quantum systems are never at rest. This is due to the Heisenberg uncertainty principle, which tells us that even at absolute zero, atoms and molecules retain some vibrational motion. But it's not just atoms and molecules. The empty space of the vacuum also has these properties. According to quantum field theory, the universe can be thought of not as isolated particles, but as continuous fluctuating fields. These fields include matter fields whose quanta are fermions like leptons and quarks, and force fields whose quanta are bosons such as photons and gluons. And guess what? All these fields have zero-point energy. These fluctuating zero-point fields lead to a kind of reintroduction of an ether in physics. However, this isn't the ether of old, a physical medium filling space. Instead, this new concept of ether is Lorentz invariant, meaning it doesn't contradict Einstein's theory of special relativity. Think of it as a modern twist on an ancient idea, seamlessly integrated into our current understanding of the universe. So why does this matter? Because these zero-point fields can be detected and have real, measurable effects. This brings us back to the Casimir effect, the Lamb shift, and even the behavior of black holes. Zero-point energy isn't just a theoretical curiosity, it's a fundamental aspect of reality that influences everything from the smallest particles to the vastness of space. Enter quantum field theory, a framework that revolutionizes our understanding of the universe. So what exactly is quantum field theory, or QFT? Imagine that all fundamental fields, like the electromagnetic field, are quantized at every point in space. Picture space as filled with interconnected vibrating balls and springs. The strength of a field is like the displacement of one of these balls from its resting position. According to QFT, changes in the strength of these fields propagate according to specific wave equations. This is where it gets really interesting. Each of these ball-spring combinations must be quantized, meaning the field strength is quantized at every point in space. Think of it as placing a quantum harmonic oscillator at every point. These field excitations correspond to the elementary particles we know in particle physics. So even the vacuum, the so-called empty space, has a vastly complex structure. All calculations in QFT must be made in relation to this intricate model of the vacuum. The theory even considers the vacuum to have properties similar to particles, like spin or polarization in the case of light, energy, and so on. But don't worry, most of these properties cancel out on average, leaving the vacuum empty in the traditional sense. However, there's one crucial exception: vacuum energy, or the vacuum expectation value of energy. The quantization of a simple harmonic oscillator requires the lowest possible energy, known as zero-point energy, to be 1-2. Summing over all possible oscillators at all points in space gives us an infinite quantity. To handle this infinity, physicists argue that only differences in energy are physically measurable, much like potential energy in classical mechanics. This concept forms the basis of renormalization theory. This is how infinities are managed in practical calculations. But there's another fascinating aspect. Vacuum energy can be thought of in terms of virtual particles or vacuum fluctuations. These are particle-antiparticle pairs created and destroyed out of the vacuum. Though they usually annihilate each other quickly, these particles can interact with others before disappearing. This complex dance can be mapped using Feynman diagrams. Note that this method of computing vacuum energy is mathematically equivalent to having a quantum harmonic oscillator at each point, which brings us back to the same renormalization challenges. Mind-blowing, right? The quantum realm is full of surprises and complexity. Now that we've ventured through the intricacies of quantum field theory and vacuum energy, let's take a bold step into a groundbreaking concept: the field strength of vacuum energy and its relationship to gravity. This theoretical study delves into the nature of the vacuum and its gravitational interactions. Imagine a mathematical framework where the field strength of vacuum energy serves as an indicator of the resistance of space-time to localized curvature. This idea challenges our traditional understanding of gravity. It suggests that the gravitational constant, g, may not be a universal constant after all. Instead, it could be a parameter dependent on the field strength of vacuum energy. Determining the value of g has been a topic of extensive research. Numerous high-precision experiments have been conducted to measure its exact value. However, these experiments have shown significant inconsistencies, puzzling scientists and calling for alternative explanations. To test the theoretical predictions regarding the field strength of vacuum energy, specific experimental conditions involving the position of the Moon have been recommended. These conditions aim to achieve consistent outcomes in precision measurements of g. The ultimate goal of such experiments is to either falsify or confirm this revolutionary theoretical framework. If validated, this concept could revolutionize our understanding of gravity and its interactions. The mysteries of the universe continue to unfold before us, revealing new layers of complexity and wonder. Stay tuned as we keep pushing the boundaries of knowledge and exploring the fundamental forces that shape our reality.